that the sum of the integrals of the absolute values, right, is less than infinity. This is what you get from saying f is represented by f1 plus f2 among other things, yeah? So we would like to check that the sum, so we're looking basically at the integral of, let's say fj plus gj, right? If we take that, well, he's not saying all this. Oh well, I'm saying too much. My point is that then this would be, less than or equal to the integral of this. And I think I could put the integral both places here. And anyway, long story short, I think you can see that then the sum n equals 1 to infinity of like the integral of parentheses fn plus gn, I mean absolute value of that guy, right? Well, that's going to be less than infinity because it's these are both when we add them. What I'm trying to say is if I take if I form finite sums of these, then I have the finite sum of this, I have the finite sum of these two is less than or equal to the finite sum of this plus the finite sum of that. But then I know that in the limit as the finite sum size goes to infinity, I know that both this and that are finite. Consequently, this, which is smaller, is also finite, which just goes to show you that we'd like to define, basically what I'm arguing is that this is in fact a reasonable definition, because if you know that the series of the absolute values of each of the step functions is less than infinity, that follows if you add them together it's still less than infinity. So in short, f plus g is an element of what? Yeah, f plus g is an element of L1. So it's a Lebesgue integrable. And how are we going to define like scalar multiple? So lambda f, right, is going to be like that. We're going to represent that by lambda f1 plus lambda f2 and so forth, Again, if you look at the partial sums of the corresponding integrals, it's going to be less than infinity because the integral of f, the integral of the absolute value of f step functions is less than infinity. So I don't think I've written enough quite to prove it, but you can see how to prove it, I think. Then what? What else so allegedly, this is a vector space. That's what I've talked about. Now, I guess to really prove it's a vector space, I need to do what? Prove that the axioms hold, but I suppose that's clear enough in terms of, you have the zero function is the sum of the zero. I mean, zero function is agreed upon to be a step function for the sake of, let's say the zero function is, well, the zero function satisfies the criteria of Lebesgue integrable, right? So it's in there. And of course, if the function, is Lebesgue integral, negative the function is also Lebesgue integrable, right? So you have that. This feels like a homework exercise I'm talking through right now. Let me stop. It feels very much like a homework exercise, yeah. But let's go on here. So, okay, so he also says that the integral of f plus g, right, is going to be what? How do you define the integral of f plus g? Well, it is defined to be the sum, right? N equals 1 to infinity of what? The integral of f plus g n, right? But the nth step function of f plus g, we're essentially defining that to be, you know, this is essentially what I was arguing before in a different notation, is the definition. The nth step function for f plus g is the nth step function for f plus the nth step function for g. And then this is just equal to, right? So this goes back to just calculus 2, really, because I'm taking two convergent series. Okay, I mean, it's calculus 2 once you put an x in. Once you put an x in, we're talking about a convergent numerical series, and these are, at any given x, these are both convergent, right? So the sum is also convergent, and it converges to the sum of the sum. Sum of series theorem from calculus 2. But then, and my bad, what have I missed? Kind of an important thing. Integrals. So, I mean, I guess there is so this is the integral. The integral of that. Integral of that, which then is actually this. Because that was one of the theorems we had. The integral of the sum of step functions was the sum of the integrals. Like, this is one of the corollaries we had about step functions last section, which then is, well, that's f, integral of f, plus the integral of g. Right? And through a similar and perhaps unexciting series of logic, you can prove the integral of lambda times f is equal to lambda times the integral of f through a similar. Basically, you're stealing that identity from the corresponding property for step functions integrals. All right. He says definition. Oh, okay. What else? I guess we need the one last thing was. Let me copy his argument down. He says if f is less than or equal to g, then g minus f is greater than or equal to 0, right? Hence, the integral of g minus f is greater than or equal to 0 by lemma 2.32, which I think we did at the start of class, right? Or maybe, yeah, I think we did. I think it's the one I erased here. And then, well, this implies that the integral of g is greater than or equal to the integral of f. So, see, because, of course, he's using a couple things. Like, he's using that the negation of the function is minus 1 times the function, and then you can pull the minus 1 out of the integral by this. So you can pull the minus out of the integral, and then, of course, you have integral of g plus the integral of minus f, which is integral of g minus integral of f, and then you get this. So there's not much missing. It's just, I should stop. I feel like I'm solving a homework problem. Okay. So now he's talking about the initial definition in this section. He says, condition A does not involve f in any way. So if you go back and look at condition A, it's that the sum of the integrals of the step functions are less than infinity. F sub I is step functions. He says condition B says that f equals the sum of the series at those points where the series converges absolutely. How big is that set? If we could find a sequence of step functions satisfying A, such that the integral the series of the absolute value of fn diverges at every point of an open interval AB, then we could write f is convergent to, f is represented by f1 plus f2 da, 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 for any function f that vanishes outside of AB, since we've proved that the integral is well defined. Well, he says, since we have proved that the integral is well defined, we know such a sequence fn cannot exist. Cannot exist maybe. In fact, the series cannot diverge at every point of a non-empty open interval. Actually, we can prove more. Oof. I guess I better write that down. Ah. Rats. I think I better write again A and B from the definition to make this conversation more understandable. Yeah. So A was that the sum n equals 1 to infinity of the integral of the absolute value of fn was less than infinity. And B was that f of x is equal to the sum n equals 1 to infinity of fn of x for each x in R for which the sum n equals 1 to infinity of the absolute value of fn of x is less than infinity. All right? So these are the conditions for Lebesgue integrable, right? And what he's currently talking about is what if you somehow had a sequence of functions, right? He says, like, hypothetical, if you could find fn such that the series fn, the absolute value of fn, n equals 1 to infinity, diverges on, let's say, open interval from A to B, then f would be represented by f1 plus f2 plus da 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 dot for any function which is 0 outside AB. See, because I mean, we can, if it's not already the case, right? If it's not already the case, we can take these functions and make them identically 0 outside AB. So if they're identically 0 outside AB, then they're automatically going to represent the function f, which is 0 outside AB, right? And yet, inside AB, this condition is not met, so they don't have to represent f. So this would be annoying if such a sequence of functions existed. This would be in fact, very annoying. But he says, we know such a sequence cannot exist. He says, in fact, the series cannot diverge at every point in a non-empty open interval. He's like, this, basically his argument is, you know, this is an unjustified worry. This, in fact, this can't happen. It's like this cannot actually happen. It cannot occur. Now, he says more though, okay? He says, here's the claim. What is it? Oh, yeah, it's okay. I haven't done much. If f, he says this, if f is f1 plus f2 plus dot 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 dot, all right? And z is equal to x in the reals such that the series n equals 1 to infinity of absolute value of fn of x diverges. Then the integral of the characteristic function of that set is 0. Now he doesn't call it characteristic function of z, he just calls this thing g, and he says, so, you know, he says this, he says f plus g is equivalent to f1 plus f2 plus dot 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 dot, and in fact the integral of f plus g is equal to the integral of f. Let's see, he says, if the integral of g is equal to 0, then the set z must in some sense be a small set. Such a set is called a null set. We can say that the series, sum n equals 1 to infinity fnx, converges to x for all x except a null set. This type of convergence is called convergence almost everywhere. Null sets and convergence almost everywhere will be discussed in section 2.7. So here's your first run into the almost everywhere concept. Here. Now he hasn't proved this can't occur yet. Maybe that happens in section 2.7, okay? So like don't like try to see it between the lines here. It's not here. But apparently this can't happen because we've just got through proving that the integral is well defined based on straightforward theorems that were already proved about step functions. So, you know, this is one of those things that happens in math. Sometimes people come up with somewhat convincing counterexamples, and yet you think you have an ironclad proof of a theory. Well, that's you know, that's where arguments happen in the cutting edge of math. Is like we have one researcher who has got a proof in the general, and the other person's got a counterexample that they think's a counterexample, but it's just a little bit fuzzy. And that's where you'll find politics. Or collaboration, maybe both, you know. A student of mine had a situation like that. I don't know how it's gotten resolved or not. He was telling me. So, all right, so that brings us to page 48. He says, unfortunately, all we have at this time is the definition of integral, and it would be awkward to try to prove that a function is integrable by expanding the function into a series of step functions. It would be like trying to evaluate the integral from 0 to 1 of e to the x dx using Riemann sums. The reader has to be patient and let the theory develop a bit further, and then we'll easily construct non-trivial examples of Lebesgue integrable functions. All right, great. So that brings us to section 2.4. What's that?
I'm not patient.
You're not patient? Yeah. Well, that's unfortunate. But I hear you. I think we're going to stop here for today. So.